Okay, so we start with the S block here. Hydrogen, helium, lithium, beryllium, sodium, magnesium, potassium, calcium, rubidium, strontium, cesium, barium, francium, radium. Then the F block, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium. Yeah, this would just be what's in my collection, so that's why it ends abruptly there. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium. And then in the D block, we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, lutetium, hafnium, tantalum, tungsten, radium, osmium, iridium, platinum, gold, mercury. Okay, and then we finally have the F block. This is the last block. This is where the vast majority of the non-metals are and where all of the metalloids are. There's even some metals too, and unknowns as well. And yeah, so hydrogen and helium would be the only non-metals not in the P block, because they're in the S block. The only reason they're in the S block is because there's no P block in the first period. That's it. Boron, carbon, nitrogen, oxygen, fluorine, neon, aluminum, silicon, phosphorus, sulfur, chlorine, argon, gallium, germanium, arsenic, selenium, bromine, krypton, indium, tin, antimony, tellurium, iodine, xenon, thallium, lead, bismuth, polonium, acetine, radon, and that's it. All that I got in my collection. I mean, there's other highly radioactive synthetic elements in the D and P block there, and then 3 more in the F block there, but I don't have those. So 7th period D block and 7th period P block I don't have any of, but I do have 7th period F block. The vast majority of it, actually. 11 out of 14, that's like 90% or something like that. I think it's almost exactly 90%. That's 110 out of 140. That doesn't help. I can't figure it out, but yeah, I'm not good with division, but like in my head, if it's like that, or some odd number. Well, I can say this in between 10/14, which is what? 10/14 is 5/7. It's in between that and 12/14, which is 6/7. Just in between 5/7 and 6/7. Okay, that's kind of weird. Actually, it's exactly in between 5/7 and 6/7. See, that's how my brain works. I figure it out like that, which is weird, isn't it? But I don't know what 11/14 is. I would have to put it into a calculator, but I can tell you it's in between 5/7 and 6/7. That's just how my brain works. It's weird, isn't it? But yeah, so yeah, that's it. That's it for the video. You can see, here's what it looks like in the entirety of it. Yeah, it's cool. So, these are all metals except for hydrogen and helium. These are all metals, these are all metals, and these are mostly non-metals, a little bit of metalloids, and some metals. Actually, are they mostly non-metals or mostly metals? No, they're not mostly metals. But they're mostly non-metals. Oh, majority non-metal block is the only majority non-metal block is the P block. Yeah, look at this. So that means the majority of these that you see, if I had a sample of every one of these over here, actually I do in my collection. Also here, look, the majority of these are non-metals. Heliums. If you want the helium in the S block, then it has to be over there. But if you want all the non-metals together, then you have to bring hydrogen over here. So it looks weird either way. So I just put them with the S block because something like that. Unless if I want to showcase metallic character, then I put hydrogen and helium over here. But if I want to showcase blocks, then I put helium over there and hydrogen over there as well. But yeah, and then that means I don't have this here, lutetium here. I have it in the D block where it belongs. Same with lawrencium, because that's, you know, where they go. Isonium, fermium, mendelevium, nobelium, lawrencium. You can see once you actually put it in there like it's supposed to, the standard, how you're supposed to display the periodic table, the standard periodic table, which almost nobody knows what the actual periodic table looks like. It looks like this. I mean, that's an incomplete version, just my collection, but still. Obviously, you can see there's a missing piece all the way across here to Oganesson, but I don't have that. It has a 700 microsecond half-life, so ooh. That's the most stable isotope. Actually, that's the only isotope that we've ever made of that one. The star here means that it's weakly radioactive, like very weakly. Very, very weakly radioactive. The rest are significantly radioactive. The rest with radioactive symbols are significantly radioactive, is what I mean. Except the only exceptions there would be thorium and uranium, which are in the billions of year half-lives. So, okay. Oh yeah, I can talk about the breakdown of the P block even further in terms of metallic character. So in this period, we have borons, a metalloid, and then carbon, nitrogen, oxygen, fluorine, and neon are nonmetals. And then aluminum is a metal, silicon's a metalloid, and then phosphorus, sulfur, chlorine, and argon are nonmetals. Gallium's a metal, germanium's a metalloid, arsenic's a metalloid, selenium's a nonmetal, bromine's a nonmetal, and krypton's a nonmetal. Huh. And then, that's cool. Interesting. But indium is a metal, tin is a metal, unless you have gray tin, which is a non-metal, which is weird. But white tin is a metal. Antimony's and that we'll try not to get into that. That's kind of one of the anomalies of the periodic table. But antimony is a metalloid, tellurium's a metalloid, iodine is non-metal, xenon's non-metal, thallium's a metal, lead's a metal, bismuth's a metal, polonium's a metal, acetine, we don't know what the fuck that is, but radon's a non-metal. Because, you know, it's a gas and it floats around. That's why we have radon detectors, because it floats around, because it's a gas. So, yeah, I mean, yeah, it's pretty crazy. All that. And then, you know, it's all metals here. All the standard D blocks, metals. Even a radioactive one, which is technetium. Obviously, I'm just talking about my collection, obviously. There's the synthetic ones as well. I mean, technetium is synthetic, but it also occurs naturally in uranium as well, as a fission product, spontaneous fission product. Promethium would be the only radioactive one in that period for the F block. And then the seventh period F block is entirely radioactive. only 90% of that I actually have. Only 90%. Damn. Only 90%. But yeah, then we have radium and francium. Oh yeah, so all the F block there would be metals as well. Radium and francium and radium are radioactive, and S block metals. Cesium and barium are not radioactive. Neither are any of those. But they're S block metals. Rubidium, strontium, S block metals. Potassium, calcium, S block metals. Sodium, magnesium, S block metals. Lithium, beryllium, S block metals. And then hydrogen and helium, since they don't have a P block where the nonmetals would usually preside, since they don't have that, they lose the metallic luster, or at least that's a weird way of phrasing it, but the S block would lose its metallic features like it has in the rest here, because there's no P block. So it starts and ends with the S block. So it starts non-metallic and ends non-metallic. So both hydrogen and helium are non-metals. They're red. See, that's actually the anomaly of the periodic table. Is hydrogen and helium. They're just weird. It's how the P block is usually always last. Well, it's because it comes after the S block. It comes after the S block once it appears. But the S block is so small. So that's why if the S block was like 5 elements instead, then maybe the first half might be metallic. Who knows? But it's not that case. You know, it's only 2 elements. So in fact, helium would be a full shell. So that means hydrogen is close to a full shell, but also you just started a shell. So hydrogen is very weird. You just start a shell that is half full and 1 away from being full. So it's 1 full, 1 empty, and half full. It's weird. That's why I love hydrogen. Hydrogen is just so cool. But yeah, you know, bismuth, very weakly radioactive, and then suddenly it becomes radioactive at polonium, like very radioactive. 138 days for the naturally occurring one. And then it gets very, very radioactive for astatine. The naturally occurring one is less than a minute. One's about a second for 218, and then 219 is about 56 seconds. Radon is only a few days. And then francium is like 22 minutes. And then, yeah. I mean, we go back to the S block, but still, we're not even talking about blocks anymore. We're just increasing the proton number. And it's getting very radioactive, and then it suddenly gets more stable. Once you get to the 90s, it's like being divisible into 3 groups of 10, or not 3 groups of 10. In groups of 10s and 3s is what I mean. So it's very divisible. I think the more prime the number is, the more unstable it is. The more composite it is, the more stable, because they like to pair up. So if they all pair up evenly like this, then there's even more stability. The more pairs you have, like you could have 4 groups of 4 and all of them are pairs. But pairs that aren't 4 groups of 4 would be less stable than 4 groups of 4 of pairs, like would happen within thorium and uranium. I don't know about 4, but like maybe 6 and 8. There's probably something that divides into these evenly. 6, 8, 4, or 2. All the even numbers would divide, or one of those even numbers would divide into thorium and uranium. Other than just 2, actually, is what I'm willing to bet. Actually, even 90 is divisible by 5 as well. And this, I'm pretty sure, is divisible by 6, I think. I don't know. I'm just guessing. I don't actually know. But 82 is especially divisible, and the more divisible it is, the more stable. So that's why lead's so stable. That's probably why it's the last stable element. Again, I'm sort of starting to describe nuclear shells without even explaining that in detail, because I'm just talking about it. It's bringing you to the idea of nuclear shells and the magic numbers, which is why all the 90s here are evenly divisible, and they're probably quite stable. Even plutonium, 80 million year half-life for 244, neptunium, 2 million year half-life. So significantly longer than the 1600 year half-life for radium.